computation for image volumes. Let me just switch. Yeah, here. Do you see the next slide with introduction and motivation? Just to make sure that's moving. Did it work? Okay. I will assume it works. All right. Yeah. So the motivation I have is that in geophysics, for geophysical exploration, we're using seismic imaging to actually detect deposits in the underground, like salt or gas or oil, depending on the application. And to do so, there is a source that will generate a signal. So the source here is the red star. And there will be an acoustic wave or some elastic wave going through the different layers in the underground, and all reflections or back scattering will be recorded on the green rectangles, triangles here that are actually my receivers. And from the coupling of the source term and the data collecting on the receivers, I would like to be able to image the different sharp edges in the underground. So one of the very common tool used by geophysicists is reverse time migration, which is actually a cross correlation between the forward wave field, which is the field that comes from the source, and the backward wave field, that is what we actually send back from the receiver into the medium. And actually, since it is supposed to be the response to the reflection here, both signals should meet exactly where they were a scatterer, so something that will make the wave back propagate here. And the idea is that we now want to extend this notion to offset as well. So now the extended image volume is a cross correlation between indeed two signals, one that is forward from one source that we used, and a backward field that comes from a receiver, but those do not necessarily come from the same signal. So the idea would be actually to gather all these signals coming from all the sources and all the receiver we used in the experiment, and to collect this huge image volume that that will contain both the zero offset, so the reverse time migration image, which is the one that is commonly used to use the edges in the underground, and all the other offset of this. That the motivation behind it, that actually those image volume gives much more information to geophysicists, not just the edges, but if you look at the entire volume, you can also get information about the wave equation migration velocity analysis or the velocity continuation. You can also try to do some targeted imaging and also to have like image gather for quality control, saying that those information can also be extracted from the image volumes, and just require to look at either a column or the diagonal or different elements of this huge matrix that represent the image volume. So that was some work I did when I was in Vancouver with the Seismic Laboratory of Imaging and Modeling. So it was really like working with people in geophysics, trying to answer that for concrete applications. The challenge and difficulties we encounter were that actually image volumes are huge and are impossible to store or even sometimes to compute. For instance, if you have a 2D model, the image volume would be 4D, and if you bought it 3D, that was 6D. So it's really like something that is too heavy to be handled by regular computers. And also there will be a lot of computation of the wave equation for those cross correlation between the forward and backward problems. So it requires a lot of computational resources and storage resources. So we cannot hope actually be able to have such an image volume entirely. But what we try to do is actually to have all this information, but implicitly. So implicitly means that actually I just want to express this image volume as a matrix vector product. So just do matrix vector produces. Sorry. So here, for instance, if I call E my image volume for extended image volume here, I can rewrite it mathematically as the cross correlation being the multiplication of the matrix containing all the backward wave field times the matrix that contains all the forward wave fields transposed and conjugated. And now I have like an explicit formula that can put on the paper, but on the computer will be much too big to actually form by just multiplying those two matrices. And actually also just those two matrices will be very difficult to handle. So we will actually use the fact that the matrices U and V containing the wave field actually solve wave equations. So the first one solve the forward wave equation where Q is the matrices containing all the sources, and V is the backward wave field satisfying the wave equation backward. So this is the conjugate transpose here, where D are the data, so the recordings. And now we can also now try to, so here it's just an illustration of how the matrix is. So if you have a problem that has a capital N grid points in the simulation of the wave equation, the image volume now becomes n times n, so n square. So it's just really like huge. So we actually decided, so we could actually write it as a 4D tensor or a volume, but we decided actually to expand it into a matrix to have more access. Sorry, I was just switch involuntarily. So to a matrix for a better visualization of the volume. And so the idea is that instead of computing the two matrices containing the forward wave fields and the backward wave fields, we actually want to probe this entire product using sampling vectors. So we have now a sampling matrix that has only like L components, and hopefully L is small enough. And we just want to probe all the things so that we only use operator vectors or matrix vector products to build the a representation or an approximation of the image volume. So we had to choose those protein vectors and see what would be the best candidates. And starting with canonical vectors was a first idea, but actually here we only get single scattering points, and we would need like capital N vectors to be able to represent the entire image volume. So it was indeed prohibitive. So we had to find other ideas. Using random Gaussian random vectors was a nice idea because it's actually model random sources. And here again, so the question was how many vectors of that sort do we need to make sure we have enough information, we can extract enough information on this image volume. And finally, we noticed that the image volumes have very narrow information when we check the spectral decomposition of it. And that's why actually singular vectors from the singular value decomposition look to be very good candidates. And in particular, if you look at the singular value decomposition of an image volume. So here, for instance, on the left, I have the model I want to, for which I want to build an image volume. In the center, this is the corresponding image volume, which you see the dimension start being the square of the dimension of the model. So here I work with a very small model for the purpose of illustration, but in the real application, you should think that it's something much bigger. And then I made I computed the singular value decomposition, and by zooming in, I can see, for instance, that only like 10 or 15 singular values are indeed meaningful or significant to represent the image volume. So my idea is that I could use probably only the 15 first singular vectors and the singular values to represent the image volume, which would reduce considerably the cost to compute and to store the image volume or all the information I want to extract afterwards for the application. So to get the singular value decomposition, again, I want to perform only matrix vectors products because I don't want to build the entire image volume every time. So I start with like a small number of Gaussian random vectors, Like typically R would be my initial guess, like the number of singular value that would be really meaningful. And by performing this randomized singular value decomposition, at the end, the matrix U here I have would be the left singular vectors of my SVD, and V would be the right singular vectors of my SVD, and sigma is the small matrix containing only the singular values, but here only R of them. So I'm now having very thin matrices, and the sigma is actually just a very small square matrix containing only the singular values on the diagonal. So I could actually represent now this image volume just with two thin matrices and a very small matrix, which also now saves lots of computational storage. So as an illustration quickly, if I have access to the full image volume, this is the image I have on the left. And now by using orthogonal probing, or the one with the singular vectors, I can get an image as good as the one in the center, which is very comparable with the original image I want to target. And on the right, I only use, for instance, random Gaussian vectors. And typically, if I took something too random, I do not grasp the most meaningful information from the image volume. So that's why actually doing this singular value decomposition really help at least cost to get the information we're looking for. Another nice framework or application of this representation for image volume is that we can design an invariance formula, which means that if I have now performed everything for one specific model and I want to recompute the image volume for another model, I do not need to make all the computation. I can just use the inversion formula to swap from one model to another, because we have those relations here, which help moving from one model to the other. So typically that works also for the low rank representation when you decompose or split the image volume into two components, where here L and R are very thin matrices, typically the size of U and V, so the singular vectors, the matrices containing the singular vectors. And you can easily get the new component for the second model just by adding two R extra PDEs, where R was again a very small number, was the number of significant singular values. So we solve a lot of energy and effort here to get a new model and without recomputing entirely the image volume. So typically, just a quick example here. I take those two parts as models. So again, those are very small models for the purpose of the computations, but and illustration. But you should think that we could be doing that on bigger models. So I assume that the model one. So I will just zoom in here. The model one is what I know, and the model two is actually no. Model one is what I actually want to get, and model two is what I start with. This is the initial guess I have, the initial information I have, and I would like to recover model one. So if I had model one and I was doing the image volume and I wanted to get the zero offset image, I would get the image on the left. But now if I only have the model two with the data from the model one, and I do the zero offset image, I get the image on the center, which we see we can recover some of the feature, but it's clearly not the same. It's clearly not a good reconstruction. But now if I use the invariance formula to correct the center image, saying that I actually had an error in my model and I want now to switch to the other model, then I can get a very comparable solution or construction, but then at a lower cost, as if I were computing entirely the image volume again. So that was actually the idea. Yeah, so I think I was much faster than I expected because I didn't get the 14-minute warning. But okay, so I should have spoken a bit more on some slides. But anyway, so the idea is that I really wanted to find a low-rank representation to describe the image volume, but okay, it was not the exact image volume, only an approximation, because I only select a significant number of singular values, but that was possible, and that was using probing vectors, and that really allowed us to be able to access the information we wanted. Even though the initial model was huge. Also, we could also use this inversion formula to help swapping from one model to another without, again, taking the full machine and compute, again, all the image volume. So we did also a complexity analysis, so which I didn't present today because I thought it would be over time, but actually probably I could have, but anyway. So here that was actually just to emphasize on the size of the matrix compared to the number of computations we have to do compared to actually trying to compute and build the entire image volume, and we could see that it was significantly lower if we were using the low-rank representation. And finally, we also did further work. We also tried to have power iterations in the randomized SVD, which allowed us to actually even reduce, again, the number of singular values, because by doing power of matrices, we could actually have the highest singular values being even bigger and the lowest being even lower. So we had a higher contrast, and we could reduce also, again, the number of probing vectors we use. We extended it to time domain. So far only short for frequency domains, but there is also a possibility to work directly in time domain. And also there is an extension to least square. So just to improve the image volume when we have a very blurry initial guess, to make it a bit better at each step of the least square. And I thank you for your attention. I think I will stop here.
Thank you very much for the nice talk, Marie. Actually, your timing was perfect, but I saw you were on 18 of 20. I thought, I'm not going to need a 14-minute